Okay, thank you. Am I a good temperature? Volume? um, okay, so today I'm going to talk about dynamic symbolic execution of JavaScript, and in particular, I want to talk about a new set of regular expression encodings that we've developed. So JavaScript has been the language of the web since the 90s, and that kind of earned it an automatic dominance and popularity. But recently, we've seen its increased popularity in the server side through tools like Node.js, and as a client-side UI framework through tools like Electron. Unfortunately for us, though, JavaScript has long proved pretty difficult to analyze. So there's a lot of reasons for this, some of which are just that there's loads of weird design features. So we have dynamic code evaluation. On the screen, you can see that you take a string, ask the JavaScript interpreter to run it. That gives us back a function, and then we run that. Also, you have dynamic type coercion. So if you subtract an array and add that to an object and then add that to a string, the interpreter doesn't throw and just gives us this weird string as output. The JavaScript interpreter really doesn't like to throw errors. Instead, it will always try and coerce stuff to a useful type. Another issue for us is that it's a constantly moving target. So there's been a major language revision every year since 2015. And this can make it really difficult. This can make it really difficult to keep up. Our takeaway, though, is that dynamic symbolic execution still works fine as long as you make some careful design decisions. So I'm going to explain dynamic symbolic execution through the following example, but first I'll explain what this program does. First, we read an input HTML file from the file system. Next, we check if that HTML file is the empty string, and if it is, we throw an error. Then we have a regular expression replacement function, which finds all of the HTML tags in that input file, and if the tag name is name, it replaces them with the constant name on line 2. Finally, we print our modified web page to std out. And there's a bug in this program that we want to find. So dynamic symbolic execution is an automated test generation approach, whereby we continuously re-execute the program each time with a new input that's guaranteed to exercise a different control flow from the previous. So the way that this works is we start by introducing some symbols to the program. And in this case, we'll start with a symbol t and an initial test case of t equals the empty string. Next, we replace our input to the program with this symbol. So here we're replacing the file system read with t. Then we just run the program as normal. As we get to line 4, we'll test whether t is equal to the empty string. And because in our first test case, we're starting with t as the empty string, we're going to take the true case of this if condition. But here we add something to a path condition, which is a set of logical constraints along this current trace that represents all of the symbols in the trace. So we're going to add t is equal to the empty string to the path condition and continue on to line 5 where we throw. And here's where the magic of DSE comes in. We can now ask an SMT solver for another input that will take us down the else case of this program instead of the true case. So here the SMT solver gives us an input where t is not the empty string, and it just gives us a as an input. So that's our next test case. Starting with this new test case, on line 4, we'll take the else case and add t is not equal to the empty string to the path condition, and proceed on to line 8. Here, a is not a HTML tag, so we're going to say that t is not a member of that regular expression. But here's where the first problem in analyzing this program happens. We can't just give a JavaScript regular expression to an SMT solver and expect it to work. So a regular expression is a tool in JavaScript which allows us to test whether a string matches some specific format. And SMT solvers actually do include some support for regular expressions. However, JavaScript adds extensions to the regular expression specification, such as capture groups, which bind a portion of the string to a variable as it matches, and back references, which will only match if what follows is a previously matched capture group variable. And it's important to note here that capture groups and back references actually make regular expressions in JavaScript non-regular. So we can't just rewrite these extended regular expressions to classical computer science regular expressions. So before we built our encoding, we wanted to check that it was actually worth doing this. So we scanned npm.js, the largest repository of server-side JavaScript software. In 415,000 packages, we saw that 35% of them contained at least one regular expression. 20% of them contained at least one regular expression with a capture group, and 4% of them contained at least one regular expression with a back reference. Note here that whilst 4% might sound like a small number, that's still almost 16,000 packages. So we gave ourselves the following two research questions. One, how can we encode regular expressions for dynamic symbolic execution? And two, what impact, if any, does this have in practice? Because whilst we know that they're in packages, we don't know that they're prohibiting any meaningful analysis. So to encode regular expressions in JavaScript, we decided to split up these extended regular expressions into a set of classical regular expressions and string constraints. So with the HTML tag example that we had earlier, we start by saying there is a string f1 or filler1 in the language .star, which means anything 0 or more times, and that's the central piece of the regular expression. We then say that C1, or capture group 1, is a string in the language .plus, which is anything 1 or more times. Next, we say that capture group 0, or the total match for the regular expression, is a concatenation of angle brackets C1 and F1. Note here, we repeat capture group 1 to enforce our back reference rule. Finally, we say that for any string to be a member of the regular expression above, that string must equal the outermost capture group. Unfortunately, though, this encoding isn't sufficient due to a feature that we've overlooked so far, which is matching precedence. So in JavaScript's regular expressions, the order of the matching operation actually matters, and it doesn't in traditional regular expressions. So I'm going to explain this through this example. We have a star and then a question mark in a capture group. A star means the letter A repeated 0 or more times, and a question mark means A or the empty string. But what we haven't thought about so far is that a star in JavaScript is actually a greedy operator, so it will consume as many A's as possible before moving on to the next part of the match. So if we encode this as before, we end up with capture group 0 equals F1 plus C1, where F1 is in the string A star, in the language A star, and C1 is in the language A question mark. But actually, C1 isn't in the language A question mark. It can never be A, because of this hidden implication that that F1 will consume all of the A's, so C1 will always be the empty string. And that means that our encoding is over-approximate. So to remedy this, we use a guided refinement loop. So as before, we use an SMT solver, but instead of just accepting the answers it gives us, we generate a candidate solution. So here we have C0 is AA, C1 is A, and F1 is A. Now we pass it to the regular expression matcher of our concrete interpreter, because we're running this dynamically, and we ask it if its expectations for C0 and the real regular expression match with our candidate solutions. And here it rejects it, because it expects C1 to be the empty string. So now that we've rejected this solution, we can guide ourselves towards a better solution. So we add a refinement that if C0 is AA, then C1 must be the empty string, and F1 must be AA. And now when we ask the SMT solver for a new candidate, it generates a correct solution of C0 is AA, F1 is AA, and C1 is the empty string. The regular expression matcher agrees, and so we can accept this and add it to our test case queue. Now that we've got this encoding, we can continue analyzing this program. So the previous test case we were looking at isn't a member of the regular expression because it's not a HTML tag. So we just continue on and print the unmodified web page. However, now we can use our encoding to ask the SMT solver for a string that does match the regular expression, and it gives us a HTML tag with the name A. In this new test case, we'll actually enter the regular expression replacement function because now we have a string that is a HTML tag. When we do that, we'll test whether the capture group 1 has the name, so the capture group 1 maps to the HTML tag name. And because we have the tag name A here, we're going to take the else case and print the unmodified web page again. But finally, because we support capture groups, we can now ask the SMT solver for a string that matches that regular expression and has the capture group 1 name of name. And it gives us the HTML tag name. On line 11, we now take the true case. And on line 12, the program crashes because we misspelled the name variable on line 2. So now we've found all the bugs in this program and explored all the possible test cases. To answer our second research question, we performed a scaled analysis of several large JavaScript packages and then a larger evaluation. So we found that in regular expression heavy applications, we saw dramatic increases in the performance of, in program coverage. In some cases, we saw up to 13 times the original coverage. Note here that these are not insignificant libraries. So the ones on screen have between 8 million and 20,000 weekly downloads. So it's pretty important that we can analyze them properly. We also did a larger evaluation of 1,131 applications where we knew we could find at least one regular expression with an automated harness, and we saw coverage increases in over half of them. Breaking this down further, we split our encoding up into basic support, that's stuff we could rewrite into classical regular expressions, then capture groups and back references, and the refinement loop. We see that each component of our encoding provides some advantage over the previous. And when the component is able to improve coverage, it improves it meaningfully. Also, we only saw a 9% slowdown between full support for these regular expressions and no support on average, which is quite acceptable for dynamic symbolic execution. I'd just like to mention that whilst I've glossed over a lot of the features of regular expressions for this talk, our actual implementation supports all of the ES6 regular expression features, including things like anchors, assertions, and flags, which are pretty tricky to deal with in practice. So in conclusion, regular expression support is essential for real-world JavaScript program analysis. Previous regular expression support was insufficient. Capture group support and back references hadn't really been addressed before, and nobody had considered that matching precedence was going to become an issue. We think that SMT plus a refinement loop provides a reasonable generic solution to this problem. I'd also like to mention that all of the work presented here is open source and available at the address below, including our dynamic symbolic execution engine Expose. Thank you.
Questions for our speaker?
Hi, very nice work. Thank you for your talk. Have you considered using this analysis to look for string taint flow sorts of vulnerabilities, something like a cross-site scripting or a path traversal vulnerability? It seems that often people will use regular expressions to do sanitization. For instance, they'll try to replace angle brackets or dot dot or something like that to make themselves safe from these vulnerabilities. It seems like your analysis would be well placed to recognize cases of insufficient sanitization. Is that something you've thought about or looked at?
Yes, we've considered using it to try and check whether validation regular expressions are correct, but not specifically for cross-site scripting or anything. Yeah, definitely I think it would be a cool thing to do.
Thanks.
So we have plenty of time for more questions.
Hey, nice work. To what extent is all of this specific to JavaScript? So other languages also have regular expressions that are non-regular. So how difficult or easy would it be to adapt this to another language?
So we tailored it to JavaScript because that's what we have the DSE engine for. So certainly most regular expressions are, most major languages have regular expression engines that are very similar to, but slightly different. And I think with small amounts of tweaking, you could use basically the same encoding. There's one exception to that. So I think Perl has recursive regular expressions, and I have no idea how you do that.
Cool. Thanks.
Any other questions?
You from some regular expression you can extract like these capture groups and like use them in your application. Do you iterate over possible extractions with different regular expressions, or you just target much or not much?
So you can have constraints on, like you could take the capture group of a regular expression result and then have a further regular expression on that. Yeah. It would make the refinement loop less effective, but the core encoding supports it.
Thank you.
So we have time for one more question. So, well, okay, I'll ask you something. So, it seems that the coverage increased significantly. Were you able to find any bugs in the applications that you look at?
So we found, we weren't really looking for bugs because in JavaScript, programs throw all the time and we don't have type expectations when we generate our harnesses. But we found at least one bug in Minimist, which has like, I think 30 million weekly downloads. So yeah, it's like an argument parser. There was a regular expression that was overly overlaxed. So yeah.
And I guess one more question. Do you observe any cases are you aware of any further opportunities to increase coverage based on regular expressions? So any corner cases that you could add?
So for us, this work is relatively complete, but I know that the string solving community is now trying to optimize for edge cases of this. So they might be able to improve the performance of DSE engines for specific subsets of these regular expressions. And then if they did that, we could get better coverage and explore more of the program and hopefully find more bugs.
Great. Well, thank you. Let's thank our speaker.